Section 7.2 continues our discussion about sampling distributions and talks about sample proportions. After this section, you should be able to find the mean and the standard deviation of a sampling distribution of a sample proportion, determine whether or not it is appropriate to use normal approximations to calculate probabilities involving the sample proportion, calculate probabilities involving the sample proportion. It's easy because it's just like normal calculations that we did back in Chapter 2. And evaluate a claim about a population proportion using the sampling distribution of a sample proportion. How good is a statistic p-hat as an estimator of our parameter p? The sampling distribution of p-hat answers this question. Consider the approximate sampling distributions generated by a simulation in which a simple random sample of Reese's Pieces are drawn from a population whose proportion of orange candies is either 0.45 or 0.15. What do you notice about the shape, center, and spread of each? For this first example, you can see at the bottom, the sample size is 25, the number of samples taken is 400, and the true population parameter is 0.45. They call it pi here instead of p. You can see the p-hat for one of those samples ends up being 0.48. If I graphed all 400 samples, the plot would look like this. Here's an example where the p-value is still 0.45, but this time the sample size is 50. Take a look and compare the shape, center, and spread of these graphs. Now let's switch the population proportion to 0.15. Here's that same example of taking a sample size of 25, 400 times, with a p-value of 0.15. For one example, you can see the p-hat value ends up being 0.24. If I were to graph the 400 samples, it would look like this. And taking a sample size of 50, 400 times, with a p-value of 0.15, gives me this graph. What did you notice about the shape, center, and spread of each sampling distribution? Well, hopefully you noticed the shape in some cases, the sampling distribution of p-hat can be approximated by a normal curve. This seems to depend on both the sample size n and the original population proportion p. The center, or the mean of the distribution, is mu sub p-hat is equal to p. This makes sense because the sample proportion p-hat should be an unbiased estimator of p. Spread. For a specific value of p, the standard deviation sigma sub p-hat gets smaller as n gets larger. The value of sigma sub p-hat depends on both n and the value of p. There is an important connection between the sample proportion p-hat and the number of successes x in the sample. The p-hat value is equal to the counts of successes in the sample divided by the sample size, or abbreviated as x divided by n. In Chapter 6, if you remember, we learned the mean and the standard deviation of a binomial random variable are given by these two formulas. Mu sub x is equal to n times p, and sigma sub x is equal to the square root of n times p times 1 minus p. Since p-hat is equal to x over n, I could think of that as x times 1 over n. We are just multiplying the random variable x by a constant 1 over n to get the random variable p-hat. Therefore, mu sub p-hat would equal mu sub x, which is n times p, times 1 over n. Notice the 1 over the n and the n would cancel out, leaving p. So p-hat should be an unbiased estimator of p. Sigma sub p-hat would equal 1 over n times the square root of n times p times 1 minus p. If I wanted to put the 1 over n inside of the radical along with the other expression, I would need to square it to put it back inside of the square root. Then one of my n's would cancel, leaving me with the square root of p times 1 minus p, all divided by n. Notice as the sample size increases, the spread will decrease. We can summarize the facts about a sampling distribution of p hat as follows. Now this will be our sampling distribution of p hat. When we choose a simple random sample of size n from a population with size capital N with a proportion p of successes, we're going to let p hat be the sample proportion of successes. Then the mean of the sampling distribution of p hat is mu sub p hat is equal to p. So the sampling distribution mean will equal the proportion of the population. The standard deviation of the sampling distribution of p hat is sigma sub p hat is equal to the square root of p times 1 minus p all over n. This standard deviation will only work as long as the 10% condition is satisfied. Again, I like to think of this as the population must be greater than or equal to 10 times the number in the sample, instead of the way it's written here. Now, as n increases, the sampling distribution becomes approximately normal. Before you can actually perform normal calculations, though, you must check the rule of thumb condition number 2, which is the normal condition is satisfied if n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10 as well. Again, those conditions, both the population is greater than or equal to 10 times the number in the sample and the rule of thumb 2 that's given here for the normal conditions was given in chapter 6. So here's kind of what we're looking at again. I've got a population proportion p of successes that's known. If I continue to take simple random samples of size n to get my p hat values and graft all of them, all possible combinations, I'm going to end up with a normal distribution as long as the rule of thumb number 2 works, the mean that would be equal to p, and a standard deviation that's the square root of p times 1 minus p all over n. Inference about a population proportion p is based on the sampling distribution of p hat. When the rule of thumb number 2 is met, the sampling distribution of p hat is going to be approximately normal. So let's take a look at this example. A polling organization asked a simple random sample of 1,500 first-year college students how far away their home is. Suppose that 35% of all first-year students actually attend a college within 50 miles of home. What is the probability that a random sample of 1,500 students will give a result within 2 percentage points of this true value? So stating what I'm trying to find, we want to find the probability that the sample proportion will fall between 0.33 and 0.37. That's 2 percentage points from 35%. The plan. Since we have a simple random sample of size 1,500 drawn from a population in which the proportion p is given as 0.35 that attend a college within 50 miles of home. To do this, I would need to find the mean and the standard deviation of the sampling distribution of p hat. Remember, mu sub p hat will equal the p-value, so that's equal to 0.35, and the standard deviation of p hat will equal p times 1 minus p divided by n, which ends up being 0.0123. Now, can I use normal calculations on this? I can, as long as n times p and n times 1 minus p are both greater than or equal to 10. Well, if I take 1,500 times 0.35, I end up with 525, and n times 1 minus p ends up being 975. Since both are greater than or equal to 10, we are going to standardize and use table A to find the desired probabilities. In doing this, for 0.33, I would get a z-score of negative 1.63, and when I standardize the value of 0.37, I end up with a standardized value z of 1.63. Now, in using table A to find the probabilities, I end up with the probability of 0.9484 for a z-score of 1.63 and a probability of 0.0516 for a z-score of negative 1.63. And subtracting these, I end up with 0.8968. My conclusion then, turning this into a percentage, it's almost 90%. So my conclusion is then, about 90% of all simple random samples of size 1,500 will give me a result within 2 percentage points of the true population proportion. In summary, when we want to know information about a population proportion P of successes, we often take a simple random sample and use the sampling proportion P hat to estimate the unknown parameter P. The sampling distribution of P hat describes how the statistic varies in all possible samples from the population. The mean of the sampling distribution of P hat is equal to the population proportion P. That is, P hat is an unbiased estimator of P. The standard deviation of our sampling distribution of P hat is equal to the square root of P times 1 minus P divided by N for a simple random sample of size N. This formula can be used as long as the population is greater than or equal to 10 times the number in the sample. The standard deviation of P hat will get smaller as the sample size N gets larger. When we have a sample size N is large, the sample distribution of P hat is close to normal with a mean of P and a standard deviation of sigma is equal to this square root of P times 1 minus P divided by N. In practice, we use normal approximations when both N times P and N times 1 minus P are both greater than or equal to 10. That means the normal condition is met. In section 7.3, we will look at sample means versus sample proportions.